the introduction. So let me first show you how to use the field theory to derive the boundary properties of all these SPD states. So I already showed you how to do that in one dimension, but now let me do 2D and 3D. No, the symmetry are listed before.
I see. Something like RV.
No, you can also do SU2, SO3. It's fine. But if you do like SU10, it's probably neither. Yeah, as long as you consider a group that can be embedded into SO3 cross time inverse or SO5, depending on dimension, then it's okay. If you consider SU10, something like that, it's probably gonna. You need a different manifold.
I'm wondering, so in 3 plus 1D, how about this symmetry for Z2 fourth power, like 4Z? So in that case, you compare to SO5.
Yeah, SO5 contains a lot of Z2 subgroup. Yeah.
But the commodity class of SO5.
No. You break the symmetry down to a smaller group, you can get more states, not less states. Right? Because SO5 will require all the n will transform into each other, but if you break down to Z2, 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 you have many different kind of transformations. Right? That's why for SO3 symmetry in one dimension you get Z2, but for Z2 cross Z2 cross Z2T you get like 16.
So if we write down this SO5 now in ESA model in 3 plus 1D, if we don't break the symmetry for the classification, it's Z2 or Z?
That should be Z2. Yeah, should be Z2.
Then you break down
you get many more. Yeah, because actually, you have many choice of operating those Z2 on those 5 component vector. Yeah, it's going to be quite hard to calculate all those. I mean, it's a big list.
For this, for lack of 4D case, I'm wondering because there's a phase that this string carrying non-linear statistics. So I'm wondering that kind of case can be.
That I haven't checked. Yeah, I haven't checked. Sorry. Yeah. Right. Yeah, we can discuss. I haven't checked.
Yeah, maybe a similar question is that, so in lower dimension, the component of n vector will be smaller.
Yeah.
But if you want to consider a large group in lower dimension, you simply want a small component of n vector.
Yeah, as I said.
So can you do that?
Yeah, I mean, if you do SUN, I'm pretty sure if you start with so for example, like the S2 is like a U2 mod U1 cross U1. Yeah. If you do SUN, you can start with a UN mod UM cross UN minus N manifold. Write down some, it also has pi 2 S2, pi 2 equal to Z, so you can write down some based on that. Yeah, but actually,
so basically, even for large symmetry group, you can find some kind of symmetric space.
Exactly.
Which say lower homotopic is non-trivial.
Yeah. But my suspicion is that all those states can be reduced to U1 eventually. Oh. Yeah. So those states may not be that interesting. If you break the SUN to U1 cross U1 cross U, it will reduce those states. It's not a new state. Yeah, okay, so now let me show you how to read off the, how to read the boundary information from the field theory. Okay, so this is a 2-dimensional SPD with a U1 symmetry, for example. So in the bulk, it's a theta term, and U1 acts this way. And, and this theta term, again, can be written as a West-Wheaton term on one boundary minus West-Wheaton term on the other boundary. So it means this theorem in the bulk will reduce to this theory on the boundary. This is the O4 non-sigma model with a West-Wheaton term on the boundary. And this theory is very well studied in field theory. And this theory we know gives us a conformal field theory, a conformal field with level with C equals to 1. Okay. And if I solve this 1 plus 1 dimensional field theory carefully, we are going to show that this theory is non-chiral. It contains the left moving modes and also right moving modes. But the U1 symmetry only acts on the right moving mode. It does not act on the left moving mode. Okay, it does not act on the left moving mode. Okay. This means that if I preserve the U1 symmetry, I cannot have any backscattering. I cannot have any backscattering between left and right moving mode. This means that the boundary will be protected by the U1 symmetry.
Okay, so what is U?
Oh, this U. Yeah, it's an extra. Okay, so let me go back. Okay, let me look at here. Okay, so yeah, as I said, this West-Wheaton term always is an area enclosed by the image, but you can see that the area is 1 dimension or higher than the image. Image like one dimension, and the area is 2 dimension. So to describe the area, we have to extend the x into u. So it means that u and x together will describe this disk. We have introduced one extra coordinate. So the same thing happens in higher dimension. So here, this phi is a mapping from the 1 + 1 dimensional boundary to a 3-dimensional sphere. And the 3-dimensional space is again 1 dimensional higher, so we have to introduce another coordinate u. Okay, so yeah. Okay, and this theory, if I break the u1 down to z2, it becomes a z2 SPD. And for the z2 SPD, the same thing happens. The z2 symmetry only acts on the right moving mode, but does not act on the left moving mode. So there's no backscattering allowed if I preserve the z2 symmetry. But once I break the symmetry, so the backscattering between left and right moving is allowed, then the boundary state will be gapped out. Gapped out by that's backscattering. Okay, so now the 3D example. This is a 3-dimensional example with time universal symmetry. Okay, time universal symmetry. So it's an O5 and a sigma model written this way. So the time universal will change sign of all the 5 components of n. Okay, if I change sign of all components n, these are 5 of them, so this will change sign on time universal. But there's an I here, so I also change sign on time universal. So the entire term will be invariant on the time universal. Okay, so what does this term mean? Okay, what does this term mean? Okay, so this term on the boundary will again reduce to a 2 + 1 dimensional or finite sigma model with the Western-Witten term. So what does the Western-Witten term mean? Okay, so it means that, for example, if I look at the vortex of n1, n2, for example, if I take D and E to be 1 and 2, then this part will describe a vortex of n1, n2. Yeah, and actually the fact that this n1, n2 attached with 3, 4, 5, it means that the vortex of n1, n2 will be attached with the 0 + 1 dimensional Western-Witten term of n3, 4, 5. Okay, this means that as the boundary, if I look as a 2D boundary, if I look at the vortex of n1, n2, it is always bound with a Western-Witten 0 + 1 dimensional Western-Witten term of n3, 4, 5. And we already know how to solve this theory. Okay, this theory will give you a doublet, and it's a Kramer's doublet. It means that under time and model transformation, this theory will change sign. So like t squared equal to -1. Okay. It means that as the boundary, the vortex of n1, n2 will carry a Kramer's doublet. For the same reason, the vortex of n3, n4 will also carry a Kramer's doublet. And this theta term as the boundary becomes a Western-Witten term tell us that if I take an n1, n2 vortex and take an n3, n4 vortex, I do a braiding, I will get a minus sign. It means that these two vortices will behave like the E and M excitations in the Topological model. Okay. This means that in the boundary, if I disorder the vector n, the most natural state I will enter is the Z2 Topological model, and the E and M both carry a Kramer's doublet. Okay. And this state is called the ETMT state. ETMT state. First, this word was first invented by Cenke and Xu. Okay. So now let's compare bosonic SPT and a fermion SPT. We know that a fermion topological insulator, the boundary, the most natural boundary, is a single cone Dirac fermion. Okay, that's the most natural boundary. So now I tell you that the most natural boundary for all these 3-dimensional bosonic SPT is a Z2 topological order. And the difference between this boundary Z topological order with the ordinary topological order is that here the E and M both carry certain non-trivial quantum number. Okay, in this case, E and M they are both Kramer's doublet. Okay, but in the ordinary Topological model, E and M they are both trivial, and in some spin liquid, E is non-trivial but M is trivial. Okay, that's the distinction between the boundary Z2 topological order and an ordinary 2D Z2 topological order. Okay, so the most natural boundary state of the 3D boson SPD is this kind of Z2 topological order with you just assign the Z2 transformation on those ends, and then the ENM will also carry some quantum number of those Z2, but fractionalized ones.
But in that case, I remember there's a paper by Lucas and Xie. They claim it's some semia on this.
You mean they are double semia theory?
Yes.
It could be. It could be. That I need to check. That I need to check. Yeah. That I need to. I forgot whether the calculus myself or not. That I need to check. But I won't say that if you assign the Z2, probably you're right. Because actually, if the Z2 will operate on both of them, actually the Y sum will be a will be a bound state between these ENMs. This will be different. That's something we have to check.
But can you also include this like half VA to this beyond the
Oh, that we can. So these kind of non-sigma models, as I said, they describe the same state as all the group cohomology. So I cannot have, but but we have a different non-sigma model, which I will talk about tomorrow. That will include those beyond cohomology state. Yeah, that will include the state. Yeah, but so far, so theory like this only describe the state within the group cohomology. Okay, so now
can I ask a question
Sure.
here? I'm a little bit confused. So the what about N1, N5 order systems?
yeah, but then you can also do that, but you can only find the two voltages that have the mutual semia statistics. Right, you can pick any two, but you can only find a pair of them. You can only have a pair of them.
Even after they are disordered.
Yeah, even after they are disordered. Yeah, the specific step to do that is to condense a double vortex, because a single vortex is the Primus doublet. If you condense single vortex, you're going to break time inversal symmetry. But a condensed double vortex will not break time inversal symmetry. So you condense double vortex, you drive the system into a Z2 topological order, and this a single vortex will survive as ENM excitation of the Z2 topological order. That's the. Yeah, before the lunch break, let me show you one last thing before the lunch break. Yeah, let me show you the relation between different SPD states. Okay, so again, this is a three-dimensional SPD state with Z2 and time inversal symmetry. As I said, there are many different ways to assign the Z2 and time inversal to the vector n, but let me choose one. Okay, this one is that I change the time inversal will change sign of all the n vector, but Z2 will change sign of the first four component, but not the last one. The reason I choose this way is because I want to guarantee these actions invariant under these transformations. Okay. You can see that this action, these Lagrange are invariant under these actions. Okay, so what does this state mean? So now let me make a domain war of the fifth component. Okay, let me parameterize the n vector like this. The sine theta times the n1 to n4, and the n5 is the cosine theta. Okay. So now let me make a domain war along the z direction, which means that theta equals 0 when z goes to plus infinity, theta equals pi when z goes to minus infinity. This is a domain war of the z, of the n5 component. Okay. If I choose this configuration and I integrate over the z direction, okay, I integrate out z direction, it means that I will reduce the 3+1 dimensional theory to a 2+1 dimensional theory. And this 2+1 dimensional theory will contain only n1 to n4. And this theory looks like this. Okay. After I integrate over the third component, it will look like this. And in this theory, because n all change sign on Z2, this theory precisely corresponds to a two-dimensional Z2 SPD. Two-dimensional SPD with Z2 symmetry. Is that clear? What I did is that I choose the configuration for n5 and I integrate over the z direction. So I only have a two-dimensional theory. And the reduced two-dimensional theory precisely becomes a 2D SPD with Z2 symmetry. Yeah. Then this means that this 3D SPD with a Z2 cross time inversal symmetry can be constructed by decorating the Z2 time inversal domain wall with a two-dimensional Z2 SPD state. Okay. Is that clear? I can first break the time inversal symmetry, and I insert a two-dimensional Z2 SPD on the T-breaking domain wall, and then I proliferate the T-breaking domain wall. Then I get this three-dimensional SPD. So this means that, this kind of a higher dimensional boson SPD, they are not so different from lower dimensional SPD. They are just constructed by inserting lower dimension SPT into some defect, and then I proliferate defect, then I get a higher dimension SPT. So this field theory describes this kind of a decorating domain or decorating defect picture. Okay. Let me show you another example. So this is a 3D SPT with U1 and a time inversal symmetry. Okay. Again, we have different choices of how to assign those U1 time inversal symmetry to this theory. So the first option is this. I do a time inversal chain sign of all the components, but U1 will rotate N1, N2, and also N3 and 4. Then this theory, if I make a time inversal domain wall, if I make an N5 domain wall, I can see that the domain wall will contain a two-dimensional SPT with a U1 symmetry in it. Okay. This is the one state. Another state corresponds to a different symmetry action. I can also choose time inversal chain sign of all the N components, but U1 rotate only N1 and 2, but not 3, 4, 5. Okay, but not 3, 4, 5. So what does this state mean? Turns out that this state, if I create an N1, N2 vortex line, then along this vortex line, the one-dimensional object, okay, along the vortex line, this means this term will reduce to a 1 plus 1 dimensional O3 non-sigma model with a theta 2 pi. And the 3 components correspond to N3, N4, N5. Can you see that? If I make a vortex of N1, N2, if this is N1, N2, make a vortex, then this term becomes a non-sigma model theta term for N3, 4, 5. And we know what the theory looks like. So it means that this state corresponds to, a superfluid phase, but I attach every vortex line with a one-dimensional Hordane phase. Then I proliferate the vortex line that corresponds to this. It's a decorated vortex line construction for the three-dimensional SPT. Okay, so this means that this kind of sigma model not only gives you the boundary property, it also shows you how we actually constructed this theory. It gives you a physical construction for all these SPT. So they are not mysterious at all. They all correspond to, almost all of them correspond to, take some defect, decorate some lower dimensional SPT, then proliferate defect. Okay. And the field theory tells you precisely the physical meaning of all those. Okay, I think it's a good time for me to let you guys take a lunch break, and we will continue in the afternoon.
Just a reminder, so we will resume at 2 o'clock instead of 1:30, and